In this video, we're going to look at a series of problems from the textbook which are designed to prove the complex conjugates theorem. Alright, the first problem in this series is number 31, where we are to prove that the conjugate of x plus z equals the conjugate of x plus the conjugate of z. And we were given that x would equal this complex number, z would equal this complex number, and therefore the conjugate of x would be r minus si, and the conjugate of z is u minus vi. Starting with the conjugate of x plus z, we will rewrite x and z as their complex expressions. We will then use associative and we will factor out the imaginary unit. And by definition of the conjugate, our plus becomes a minus. So this is now our real part, this is our imaginary part. Here we will distribute our minus sign and our imaginary unit, and then we will use commutative property and associative property again, and we now see that we have r minus si and u minus vi being added together. So our conclusion is that the conjugate of a sum, which we started with, is equivalent or equal to the sum of the conjugates. Number 32, given the same information for x, z, and conjugate of x, conjugate of z, we are to prove that the conjugate of the product xz equals the product of the conjugates. Starting with the conjugate of the products, let's rewrite x and z as their complex expressions being multiplied, and we are implying that we will take the conjugate of this product, perform multiplication, and by associative property and simplification and factoring out the imaginary unit, we get this expression. And again, our definition of a conjugate is that our plus becomes a minus. And now in this proof, I'm going to start with product of the conjugates and work to obtain this same conclusion. X and z we replace with their complex forms, and this conjugate for r plus si is r minus si, and likewise the conjugate of u plus vi is u minus vi, and then we will multiply. After multiplication, combine like terms, factor out the imaginary unit, and we have shown that these two conclusions are exactly the same, and so therefore we've proven that the conjugate of a product is in fact equal to the product of the conjugates. Number 33. Now for some of these problems I had some notation issues here, but just know that this is the conjugate of x squared, and we want to show that that will be the square of conjugate of x. So let's start with the conjugate of x squared. X is r plus si, so this is the conjugate of r plus si squared. And I'll go in a minute and I will add our conjugate notation here, but all I did was multiply out r plus si times itself. And then after simplification, we can designate this as our real and this is our imaginary for this complex number. These should have our conjugate notation, and the definition of conjugate is our plus becomes a minus. So this is our conclusion for one half of the proof. On this side of our proof, I'll perform some steps which will lead this to this expression. Again, when I'm all finished, I'll draw in all of our conjugate notation for all the steps that should have it. But conjugate of x was given as r minus si. So multiply that out, then combine like terms, and we have our real and our imaginary. And again, we've achieved the same thing on both sides of this proof. And again, this was a conjugate, this was a conjugate. And what we have shown is that the conjugate of a square is equal to the square of the conjugate. Now, number 34, we are to prove that the conjugate of x cubed will equal the cube of the conjugate of x. Let's start with the conjugate of x cubed. Rewrite it as a product. From number 32, we determined that the conjugate of a product is the product of the conjugates. In 33, we proved that the conjugate of a square is the square of the conjugates. And so our conclusion is the conjugate of a cube is the cube of the conjugates. 35a, we are to prove that the conjugate of a real number a is itself a. So a can be written in complex form as a plus 0i. And if I want the conjugate of a, I would be taking the conjugate of a plus 0i, which is a minus 0i. We don't need to write minus 0i, so what we've determined is the conjugate of a is a. 35b, again this is supposed to be one conjugate, and we want to show that the conjugate of ax cubed is equal to a times the conjugate of x cubed. So let's start with the conjugate of ax cubed. A, the real number, can be written as a plus 0I. And from a previous problem, we showed that the conjugate of a product is the product of conjugates. And from part A, we showed that the conjugate of A is A. And from number 34, we showed that the conjugate of a cube is the cube of the conjugate. Number 36, we're proving two things. That the conjugate of bx squared equals b times the square of conjugate of x, and that the conjugate of cx equals c times the conjugate of x. B and c are real numbers, just as in number 35, a was a real number. So let's look at the conjugate of bx squared. From 32, the conjugate of a product is the product of the conjugates. From 33, the conjugate of a real number is the real number. And from 35, the conjugate of a square is the square of the conjugate. And for part 2, same conclusion from number 32, that the conjugate of a product is the product of conjugates, and the conjugate of a real is itself. And so we have finished number 36. Number 37, prove that a cubic polynomial is equal to the same polynomial in terms of the conjugate of x. So let's start by taking the conjugate of this polynomial. And if we review back from number 31, 31 stated that the conjugate of a sum equals the sum of the conjugates, and we're using that for our first step here, number 37. The conjugate of a sum equals the sum of the conjugates. And from 35 and 36, the conjugate of ax cubed is a times the cube of conjugate x, likewise with the quadratic term and the linear term. And for our real constant, the conjugate of a real is the real. Last problem was 38. And remember, our overall goal is to prove the complex conjugates theorem on page 85, which we're very close to doing. So 38 says, prove that for this cubic polynomial, and given that p of x is 0, so x is a root, we want to prove that the conjugate is also a root. So we're going to start by doing p of the conjugate. Working backwards from number 37, let's look at 37 again. Remember, our conclusion lets us take our second step, and we were given that p of x is 0, and from 35a, the conjugate of a real is itself. So we've finished proving our complex conjugates theorem.